Jump to content. Main menu. Main menu, move to sidebar, hide. Navigation. Main page, help, browse cookbook, Wikijunitor, feature books, recent changes, random book using Wikibooks. Community. Reading room, forum, community portal, bulletin board, help out. Policies and guidelines, contact us. Search. Search. Appearance. Donations, create account, log in. Personal tools. Donations, create account, log in. Pages for Longbout editors, learn more. Contributions, discussion for this IP address. Contents, move to sidebar, hide. Beginning. 1. Noise emission of the rotor stator mechanism. 2. Optimization of the number of blades. 3. Determination of source levels. 4. Directivity. 5. Further reading. 6. External references. Toggle the table of contents. Acoustics/rotor stator interactions. Add languages. Add links. Book discussion. English. Read, edit source, view history. Tools. Tools, move to sidebar, hide. Actions. Read, edit source, view history. General. What links here, related changes, upload file, special pages, permanent link, page information, site. This page gets shortened URL, download QR code. Sister projects. Wikipedia, Wikiversity, Wiktionary, Wikiquote, Wikisource, Wikinews, Wikipedia Commons, Wikidata Media, Wiki, MetaWiki. Print/export. Create a collection, download as PDF printable version. In other projects. Wikidata item. Appearance, move to sidebar, hide. From Wikibooks, open books for an open world. Acoustics. An important issue for the aeronautical industry is the reduction of aircraft noise. The characteristics of the turbomachinery noise are to be studied. The rotor/stator interaction is a predominant part of the noise emission. We will present an introduction to these interaction theory, whose applications are numerous. For example, the conception of air conditioning ventilators requires a full understanding of this interaction. Noise emission of the rotor stator mechanism. Edit vertical line. Edit source. The rotor wake induces on the downstream stator blades a fluctuating vane loading, which is directly linked to the noise emission. We consider the B blade's rotor at a rotation speed of O_displaystyle_omega and a V blade stator in a unique rotor/stator configuration. The source frequencies are multiples of BO_displaystyle B_omega, that is 2 cm BO_displaystyle megabytes/omega. For the moment we don't have access to the source levels FM_displaystyle F_m. The noise frequencies are also MBO_displaystyle megabytes/omega, not depending on the number of blades of the stator. Nevertheless, this number V has a predominant role in the noise levels PM_displaystyle P_m and directivity, as it will be discussed later. Examples. For an airplane air conditioning ventilator, reasonable data are B equals 13 \displaystyle B equals 13 and O equals 12,000 \displaystyle omega equals 12,000 R&D/minimum. The blade passing frequency is 2600 Hz, so we only have to include the first two multiples, 2600 Hz and 5200 Hz, because of the human ear high sensibility limit. We have to study the frequencies M equals 1 and M equals 2. Optimization of the number of blades. Edit vertical line. Edit source. As the source levels can't be easily modified, we have to focus on the interaction between those levels and the noise levels. The transfer function FMPM_displaystyle F_m/over P_m contains the following part: S equals 8F equals +8E, IMB, SV page to JMB, SVMPM_displaystyle_sum. /limits_S equals \empty circumflex accent S equals plus \empty E circumflex accent by megabytes SV /pi/over to J_megabytes SVM where M is the Mach number and JMB. SV /displaystyle J_megabytes SV the Bessel function of megabytes SV order. In order to minimize the influence of the transfer function, the goal is to reduce the value of this Bessel function. To do so, the argument must be smaller than the order of the Bessel function. Back to the example. For m equals 1, with a Mach number m equals 0.3, the argument of the Bessel function is about 4. We have to avoid having megabytes SV inferior than 4. If v equals 10, we have 13 1 x 10 equals 3, so there will be a noisy mode. If V equals 19, the minimum of megabytes SV is 6, and the noise emission will be limited. Remark. The case that is to be strictly avoided is when megabytes SV can be null, which causes the order of the Bessel function to be 0. As a consequence, we have to take care having B and V prime numbers. Determination of source levels. Edit vertical line. Edit source. The minimization of the transfer function fmpm \displaystyle f_m over p_m is a great step in the process of reducing the noise emission. Nevertheless, to be highly efficient, we also have to predict the source levels fm \displaystyle f_m. This will lead us to choose to minimize the Bessel functions for the most significant values of m. For example, if the source level for m equals 1 is very higher than for m equals 2, we will not consider the Bessel functions of order to be SV. The determination of the source levels is given by the Sears theory, which will not be discussed here. Directivity. Edit vertical line. Edit source. All this study was made for a specific direction, the axis of the rotor/stator. All the results are acceptable when the noise reduction is ought to be in this direction. In the case where the noise to reduce is perpendicular to the axis, the results are very different, as those figures shown. For B equals 13 and V equals 13, which is the worst case, we see that the sound level is very high on the axis for equals 0 \displaystyle theta equals 0. For B equals 13 and V equals 19, the sound level is very low on the axis but high perpendicularly to the axis for equals pi/2 \displaystyle theta equals pi/2. Further reading. Edit vertical line. Edit source. This module discusses rotor/stator interaction, the predominant part of the noise emission of turbo machinery. See acoustics/noise from cooling fans for a discussion of other noise sources. External references. Edit vertical line. Edit source. Prediction of rotor-wake-stator interaction noise by Peasage Smith and JDHM. Shulton active control car mufflers. Active controlled acoustics car mufflers. Retrieved from https://wikibooks.org/w/index.php title acoustics/rotor_stator_ interactions and bolded 3,246,813 Categories Book: Acoustics. This page was last edited on July 27, 2017, at 2:05. Text is available under the Creative Commons Attribution Share Alike license. Additional terms may apply. By using this site, you agree to the terms of use and privacy policy. Privacy policy about Wikibooks. Disclaimers. Code of conduct. Developers. Statistics. Cookie statement. Mobile view.